2015 number 2. This is a fun little problem. You've got some ethanol that's going to be heated up and decomposed into ethene gas, and we're going to collect that ethene gas over water is what's happening here. So we have this equation, this decomposition reaction. We see a delta H at the beginning, we see a delta S at the beginning, which means spontaneity is probably going to be involved in this question somewhere. And then we get right into it. Student added 0.2 gram sample of ethanol in liquid form to a test tube using the setup shown above. They heat the test tube until all the ethanol is evaporated and gas generation stops. When the reaction stopped, the volume of the gas was this, the pressure was this, and the temperature was 305 Kelvin. It says the vapor pressure of water at 305 is 35.7 torr. And so that's going to come into play. And we've talked about this before. Anytime you collect gas over water, not only up in that top of that tube is ethene there, but we also have some water there that we have to account for because we're about to find just the moles of ethene up in the top of that tube. That's where we start on this. And so here we go. It's a little partial pressure problem before we can do PV equals nRT, but this is calculating the number of moles of ethene that are actually produced in the experiment and measured in gas collection tube. That means we're using this data to figure out moles of ethene. It's volume and pressure and temperature. That means PV equals nRT. So we have an ideal gas law problem that we're going to do. We need just the moles of ethene, which means the pressure that's 0.822 atmospheres also contains this much pressure of water, and so we've got to eliminate that pressure of water from it. So we're going to take the 35.7 torr that's given off by the pressure of water, and we're going to turn that into atmospheres. That's what we did here. And so 0.047 atmospheres are pressure from the water vapor. So our total pressure in the top of the tube equals 0.822. I think that's right, 0.822. That total pressure is going to equal the pressure of the water plus the pressure of what we want, the ethene, C2H4. And we just found the pressure of the water, 0.0470 atmospheres. We want to work all these PV equals nRT problems in atmospheres. And when we do this, that pressure of C2H4, 0.822 minus the 0.470 gives us a pressure of C2H4, the ethene, that's 0.775 atmospheres of pressure. And so that guy is what we're going to plug into our PV equals nRT. Hopefully you can see that there. And so here we go. PV equals nRT, our pressure, the 0.775. Do it in atmospheres, times the volume. They gave us a volume up here in the problem of 0.0854 liters. And that's going to be equal to, forgive me, I'm going to write it underneath, the number of moles that we're after times the ideal the ideal gas law constant, 0.0821 liters atmospheres over moles times Kelvin times the temperature that they gave us is going to be 305 Kelvin. Oh, I'm squeezing. Times the 305 Kelvin. So 0.775 times 0.084 liters divided by the 0.0821 divided by the 305 Kelvin, and our moles of ethene are going to be 0.00264 moles C2H4. That's part A, number 1. Looks like that. You can pause it there if you need to look back at that calculation. What part 2 asks us to do is it says calculate the ethene that would be produced if the dehydration reaction went to completion. And so what they're saying is if we started with this 0.2 grams of the ethanol and this reaction went to completion, how much ethene should we have produced? It's a 1-to-1 ratio up here in the equation. And so this is just a quick little stoich problem here. 0.200, 3 sig figs here, grams C2H5OH. Grams to moles, there's 46.1 grams per 1 mole of ethanol, and then moles of ethanol, C2H5OH, going to moles of ethene, C2H4. I showed you that equation in the problem a second ago. It's a 1-to-1 ratio, and so when we plug this guy in, we get that if it went to completion, we should have gotten 0.00434 moles of ethene. So all that ethanol that got heated up and evaporated, some of it didn't decompose. And so if all of it decomposed, we would have gotten this much ethene. We only got 0.00264. That's good because it's less. It's a good indicator we're in the right ballpark here. Then it asks us a percent yield problem. Calculate the percent yield of the ethene in the experiment. And so percent yield problem, easy. Percent yield, this is equal to the actual value we produced divided by the theoretical value we should have produced, all times 100. And so the 0.00264 divided by the 0.00434 all times 100 should give us a percent yield of 60.8%. This is one where we have a tendency to say, can I avoid writing the generic equation and just write the numbers in and solve for this? And I would caution against that, just because if you screwed up one of these numbers, if you don't set up generic equation and put the numbers in there, then you won't get propagation error there. So set up the generic percent yield problem. And then if you messed up one of these numbers and you plug in and you get the answer wrong there, you still find credit for it. Part C kind of takes a little turn here. So part C says, do the thermodynamic data for the reaction support the student's claim? The student claims that the reaction has an equilibrium constant less than 1 at 298. So at the beginning of this, before we heat it up at room temperature, it wants to know if this reaction is going to be spontaneous or non-spontaneous. It asks for a calculation with delta G. We know that if K is greater than 1, it's a spontaneous reaction. If K is less than 1, it's non-spontaneous. And so this is, it says include a calculation, and so we have to do a calculation for delta G here. So here comes the delta G calculation. This is where the delta H from up top comes into play. So delta G equals delta H minus T delta S. And we're stealing the data from up here in the top of this reaction. So here we go. Delta G is going to equal, and I'm stealing that data as well, 45.5. Units, be careful. That's kilojoules per mole on the delta H minus T delta S. Temperature is 298 Kelvin times our delta S. Our delta S units, look at kilojoules per mole here, joules here. And so we've got to take that delta S and change it into kilojoules. That makes it 0.126 kilojoules per mole Kelvin. And then we plug that thing into the calculator. Easy enough. Our delta G there equals 7.98 kilojoules per mole. This is an endothermic process. feel like it talks about that at the top. Maybe I lied. But anyway, it's endothermic. Delta H is positive, so it's getting colder. This is the favored, this is not favored, right? And so we end up with a positive delta G. It asks about the K. It says, will the K value be greater than, less than 1? And so when we look at this, in order to justify this, we have to go back and do delta G equals negative RT natural log of K. And when we do this, if we have a positive delta G, then K will be less than 1. So yes, positive delta G or delta G bigger than 0, so the reaction favors reactants. K must be less than 1. Use that equation to justify this statement that you make. Good? Good. Part D says the Lewis electron dot diagram for C2H4 is shown below in the box. In the box on the right, complete the Lewis electron dot diagram for the ethanol, drawing in all electron pairs. You should count them up. We know there's going to be at least one pair of electrons between every one of these sets of elements. Those are our pairs of electrons. So it looks like this. But I'm going to add these up and make sure. If I add these up, carbons each have 4 valence electrons. That's 8, 9, 10, 11, 12, 13. Oxygen has 6 more. That's 19 and 20. We should have 10 pairs. Right now we have 1, 2, 3, 4, 5, 6, 7, 8 pairs. We need 2 more pairs. Everything in here is satisfied except for that oxygen's octet. Oxygen has to have an octet, so there's our other 2 pairs of electrons. That should be okay for everybody. That's pretty self-explanatory. So make sure you handle that. I would do dots here instead of bars here. Save you some trouble, because that's the example looked that way. Then E says, what's the approximate value of the bond angle between carbon and oxygen and hydrogen? That's very much looking like this. And so we've got 4 domains, right, and 2 lone pairs. The approximate bond angle, just like in water, should be approximately 104.5 degrees. They took anything from 100 to 115 on this problem. I would put approximately 104.5. That would be how I would answer that question for the bond angle. If you got questions on that, shoot me an email. And then F says, during the dehydration experiment, C2H4, an unreacted ethanol passed through the tube into the water. The C2H4 was quantitatively collected as a gas, but the unreacted ethanol was not. Explain in observation terms the intermolecular forces between water and those 2 gases. And so I'm going to feed this to you really quick, and then you can come back and read through my answer. When we look at the ethanol has hydrogen bonding as a result between it and the water. And that hydrogen bonding makes it really polar. And so if it's really polar and water's really polar, then it is soluble in that water. That's why we don't see it collected as a gas. Ethene only has dispersion forces. It's a nonpolar molecule. So the only interactions it has is it has water being a dipole, and ethene gets induced dipoles with that water. But that interaction is weak, and so water being really polar and ethene not being polar creates very little solubility. And so the ethene turns into gas and doesn't dissolve back in the water the way the ethanol vapor would. That's our answer. Thanks for watching. If you got questions, yell at me.